Good evening, everyone, to the Earth and Planets Laboratories Neighborhood Lecture Series. I'm Mike Walter. I'm Director of EPL, and on behalf of all of my colleagues here at Carnegie Science, I'm very pleased to welcome you to tonight's lecture. It's my great pleasure to introduce you to Dr. Michael Wong as our speaker this evening. Mike is an astrobiologist and a planetary scientist with broad interests in planetary atmospheres, habitability, biosignatures, and the emergence of life. Mike got his PhD from the California Institute of Technology in the Division of Geological and Planetary Sciences, where he worked on computational modeling of planetary atmospheres. It was in 2018. Mike followed that with a postdoctoral position at the University of Washington, again in the Department of Astronomy and Astrobiology, where he worked on simulations of atmospheric chemistry of terrestrial planets around M-dwarf stars. Mike joined us here at Carnegie as a Carnegie Fellow in 2021. And is working to assess the network topology of exoplanet atmospheres with the aim of identifying potentially unique biosignatures. Mike was recently awarded a prestigious NASA Hubble Fellowship to continue his investigations on network topologies here at Carnegie. Mike also hosts the Strange New Worlds podcast that examines science, technology, and culture through the lens of Star Trek. And tonight, Mike will regale us with the science of Star Trek. Just to give you an idea of the lineup, Mike will speak for about 30 minutes, after which Mike will lead a panel discussion with several of our postdoctoral fellows and staff members here at EPL. That'll last for maybe another 30 minutes, and that'll be followed by questions from the audience. So take it away, Mike.
Awesome. Thank you for that amazing introduction, Mike. Hopefully everybody can see my screen at the moment. Actually, I'm going to go ahead and minimize that so that I don't have to stare at myself for the next hour and a half. So welcome everyone to the science of Star Trek. Before we begin, I want to issue a spoiler warning because in this event, we are going to be spoiling various plot points from the entire Star Trek universe, from the original series in the 1960s all the way through to the modern streaming shows like Discovery, Picard, and Strange New Worlds. And there's really no way to talk about the science of Star Trek without talking about Star Trek. So if you are extremely spoiler averse, this may not be the event for you. But that said, I hope that you all stick with us throughout this entire event because we are going to visit some incredible places and learn some amazing things. And I hope that this discussion will deepen your appreciation for the Star Trek that you may have already seen, and make you more eager to go and watch the Star Trek that you have not visited yet. And so with that, let's begin. So I always like to begin these lectures with something called Faraday's law of induction. So you may be familiar with Faraday's law. You may even remember playing around with it in science class. Generally, it's demonstrated with a coil of wire and a magnet. And what you do is you pass the magnet through the wire, and the changing magnetic fields induces an electric current in the wire. Now, when this was discovered, it helped us unify the forces of electricity and magnetism into something that we now know and love as electromagnetism. Now imagine that you could somehow unite the forces of electromagnetism with the force of gravity. And as Einstein told us, gravity is nothing more than the bending and rippling of space-time. So what if you had an electromagnetic energy source so powerful that you could literally warp the space around you, expand it behind you, contract it in front of you through the power of science, plus a little sprinkling of imagination? You will have created a tidal wave of space-time that you could surf faster than the speed of light. What would you do with such a marvelous engine? I think I know. I think you'd venture out into space, the final frontier. Explore strange new worlds, seek out new life and new civilizations boldly. Find yourself under a pile of triples. you'd be an explorer, going where no one has gone before, and all the while making new friends, sharing fond memories, and learning what it means to be human. This was the vision of a man named Gene Roddenberry, who in 1964 wrote a proposal to NBC Studios for the creation of a brand new science fiction show that he called Star Trek. Now, ever since Star Trek's inception, Gene Roddenberry knew that he wanted science to be at its core. So much so that he wrote in this 1964 proposal about an equation penned just a few years earlier by astrophysicist Frank Drake. This is what Drake's equation looks like. It's meant to help us organize our knowledge and our ignorance about the cosmos in an attempt to estimate the number of intelligent transmitting civilizations in the galaxy. The thing is, back in 1964, you couldn't just Google Drake's equation. In fact, Gene Roddenberry had no idea what Drake's equation even looked like. So under the pressure of the studio to submit his proposal on time, he simply scribbled something random onto a piece of paper and sent it in. Now, luckily, the studio also had no idea what Drake's equation looked like, and Star Trek was approved. Legend has it that many years later, Professor Drake was actually invited aboard Star Trek to scientifically advise an episode of Star Trek Voyager. And when he was on the set, he was shown this fake Drake equation that Gene Roddenberry had penned in his name. And when he saw it, he just laughed. He said, "Oh, Gene, didn't you know that raising something to the first power is simply itself? Like, why would you write that?" So here's what Drake's equation actually says. Again, it's trying to estimate the number of intelligent transmitting civilizations in the galaxy. So unfortunately, tonight, we don't have time to go through each and every one of these terms in great detail, but suffice it to say that the last four terms, those shown here in red, are really difficult to estimate. They deal with things like the probability of the emergence of life or the lifetime of a transmitting civilization. These are numbers that we have no idea what they are to this day. But the first three numbers, those shown here in blue, are astrophysical quantities. These are numbers that we can try to get a handle on through astronomical observations today. So if we take just those first three numbers and we multiply them out, we'll get the number of Earth-like planets in the galaxy. That's the number of stars in the galaxy multiplied by the fraction of those stars that are planets, multiplied by the number of Earth-like planets per planetary system. Now, Gene Roddenberry still had no idea what this number was. In the 60s, there was just no way for him to know. But he did know that whatever this number turned out to be, it was going to be huge, right? Because the number of stars in our galaxy is literally astronomical. So when you discover what this number is tonight, you are going to have a choice to make. You're going to have a choice about how you're going to feel about this number. Are you going to feel small because you're just one insignificant being on a tiny mote of dust floating in a vast cosmic void? Or are you going to feel large because you're connected to this grand evolving universe of ours, and special because despite what might be out there, despite all of those possibilities, there's still just one and only one of you? This is the kind of mathematical philosophizing that Dr. Leonard McCoy brought to his captain, Captain James T. Kirk, in an episode of classic Star Trek called The Balance of Terror. In this episode, Captain Kirk is pitted against an equally formidable Romulan captain, and he's feeling the draining weight of Starship Command. He's second-guessing his every move. He just wants a vacation. So Dr. McCoy comes to his captain to spur him back into action. And he does so by prescribing a very peculiar, though very potent medicine. and that is the mathematical probabilities of the universe. In this episode, Dr. McCoy says to Captain Kirk, in this galaxy, there's a mathematical probability of 3 million Earth-type planets, and in all of the universe, 3 million galaxies like this. And in all of that, and perhaps more, only one of each of us. Don't destroy the one named Kirk. It's a very powerful scene from the TOS episode Balance of Terror, in which Dr. McCoy claims that there are 3 million Earth-type planets in our galaxy. Well, let's see how right he was. Today, we know that there are some 200 billion stars in the Milky Way. Now, this isn't an exact number. It's just an order of magnitude estimate, but it'll suffice for our purposes tonight. Thanks to the Kepler Space Telescope, humankind's greatest planet-finding machine to date, and the TESS telescope, which will soon surpass Kepler's planet-finding record, we now know that the fraction of stars that have planets is essentially 1. And thanks to the hard work of astrophysicists around the globe, we now know that roughly 1 in 5 of those stars has an Earth-sized planet orbiting in that star's Goldilocks zone. So if you multiply these 3 numbers together, you get something like 40 billion. 40 billion. And remember, a billion's 1,000 times more than a million. So Dr. McCoy was off in his estimate by a factor of over 10,000. Yikes! But it's okay. We'll forgive Bones. After all, he'd love to remind us, damn it, Jim, I'm a doctor, not an astrophysicist. So one criticism you might make of the Drake equation framework is its requirement for Earth-like planets. It's quite possible that we need to cast a wider net in order to truly appreciate the diversity of life in the universe. In fact, I have colleagues who would argue you'd learn very little about what life actually is unless you found it in a truly exotic environment. One maybe like Jupiter. Okay, this is Jupiter. Jupiter is a gas giant planet. It's got no solid surface, no oceans of liquid water. This is not the first place you'd think of for looking for life elsewhere. But the idea of life floating in gaseous atmospheres has been around for many decades. Carl Sagan and Ed Salpeter published a seminal paper in 1976 speculating about an ecology of what they called floaters and sinkers in Jupiter's atmosphere. And just this year, in the 4th season of Star Trek Discovery, we went where no one has gone before, journeyed beyond the edge of the Milky Way, and were introduced to species 10C. These creatures inhabit gas giant atmospheres beyond the shores of our galaxy and communicate via a combination of chemical pheromones and light pulses. As an astrobiologist, I get so excited by this. I love pondering this kind of alien ecosystem. And one of the first questions that I ask is, this aerial biosphere that the 10C are a part of, that they evolved in, that they thrive in, where would it get its energy from? Well, unfortunately, I've never had the pleasure of conversing with a member of species 10C, but I do know how I am powered. I eat and I breathe, and in my mitochondria, electrons are shuttled from the food that I eat to the oxygen in the air that I breathe. And it's this transfer of electrons that powers me to do cool things, like be with all of you tonight and talk about the science of Star Trek. Now, if the transfer of electrons to power something sounds a little bit odd, I promise you it's not. It's exactly what happens when you light a piece of wood on fire or flip a switch to light a room. And so in general, what life does is that it transfers electrons from some reductant or electron source to some oxidant or electron sink. And at the planetary scale, one could say that what life does is it completes a geochemical circuit. At the very beginning of life on Earth, the two ends of this geochemical battery may have been hydrogen and methane as the electron source, and CO2 and nitrogen oxides as the oxidant. We would call this kind of life chemotrophic life or chemical eating life. Now, on the early Earth, one end of this geochemical battery would have been much more abundant. There was plenty of CO2 available in Earth's early atmosphere. So life would have had to huddle around geological sources of hydrogen and methane until it discovered a very clever trick. And that is to make its very own electron source by splitting apart water using sunlight, breaking apart an H2O molecule, resulting in hydrogen that it can use in its metabolism, and just discarding that oxygen, because back then it was useless. This is a process that we call oxygenic phototrophy. Now, the situation would be reversed on a gas giant planet because there hydrogen is everywhere. It's literally 90% of the atmosphere. You have more reductant, more electron source than you know what to do with. What life needs is to make a good oxidant. So I hypothesize that life in such an atmosphere would be incentivized to evolve a way to split water using sunlight in exactly the same way as it does here on Earth. But instead of coveting that hydrogen, coveting the oxygen that it makes through this process instead, and just spitting the hydrogen back out into the atmosphere, because who needs that on a gas giant planet? In my mind, this hydrogenic phototrophy would be the basis of an ecosystem such as the 10 Seas, or an ecosystem on any hydrogen-dominated world. So our takeaway from thinking about the 10C just a little bit deeper is that life is flux. Life runs on a flux of electrons, which necessitates a flux of gases. And what specific gases those are depend on the specifics of the environment in question. On Earth, it's one thing. On a gas giant, it needs to be something else. This is the first of our major takeaways tonight. Okay, so despite the 10C's massive ecological differences from us, biochemically, they're actually quite similar. There's this beautiful Star Trek moment where a team of scientists, medical doctors, diplomats, and linguists work together to decipher the 10C's chemical language. And they found out that the 10C communicate via hydrocarbon pheromones, just like many animals on Earth do. In fact, these pheromones even had an effect on the human members of the Discovery crew. So in the grand scheme of things, the 10C are basically just like us, carbon-based bags of mostly water. But what if there's life out there that has a completely different biochemistry from our own? Well, Star Trek has explored situations just like this in the classic Star Trek episode called The Devil in the Dark. Kirk and crew encounter the Horta, a monster that was terrorizing a colony of miners, but turned out just to be a mother trying to protect her young. This creature eluded Starfleet sensors because, as Mr. Spock explains, life as we know it is universally based on some combination of carbon compounds. But what if life exists based on another element? For instance, silicon. To which Dr. McCoy proclaims, "You're creating fantasies, Mr. Spock." Well, it turns out that Spock was right in this case, as he often is. The Horta turned out to be a silicon-based life form. Still, I think that Dr. McCoy's skepticism was justified in this case. And let me explain a little bit more about why. So people often consider silicon to be a good alternative to carbon because it has similar chemical properties. For instance, it has 4 valence electrons. That just means that it can make 4 bonds with other atoms. So for instance, here you see methane, CH4, and on the other side of the slide, you have silane, SiH4. They have very similar tetrahedral structures. But if we scratch just a little bit deeper at the chemistry, we start to run into some major problems. You see, chemical bonds are often not equal sharing endeavors. In the methane molecule, this carbon tugs on the electrons in those bonds a little bit harder than the hydrogen does, meaning the electrons in this molecule spend most of their time huddled around that central carbon atom. But in the case of a silicon-hydrogen bond, the polarity of this bond is reversed. these electrons in silane are actually going to spend most of their time on the outskirts of the molecule, making silane highly reactive. In fact, it's so reactive that it spontaneously combusts, which is probably why you've never heard of it before. You would never have gone into a place on this world where silane was a stable molecule. So, what's the first thing that engineers in Star Trek try to do when they're faced with any problem imaginable? Well, they try to reverse the polarity, right? And this is a real life example of how reversing the polarity is so crucial. It's literally the difference between a stable molecule like methane and one that spontaneously combusts like silane. Now, life also needs to constantly replenish itself with new materials, and life on Earth primarily gets its carbon from carbon dioxide, which is a gas that wafts around everywhere, is universally accessible. Now, here's CO2, carbon dioxide, and SiO2. On the face of it, they look just the same. But again, if we dig just a little bit deeper, we run into some major problems. CO2, like I said, doesn't like to react with things, but SiO2 has a propensity to react with itself, making these complex matrices. In fact, SiO2 has a more colloquial name that you may be familiar with. It's quartz. So basically, unlike carbon, silicon is pretty difficult to access by biology. Now, let me be clear. I am not saying that Star Trek was wrong for depicting the Horta as a silicon-based life form. What I'm actually trying to say is that Star Trek got it right by continuing the dialogue between Dr. McCoy and Spock like this. McCoy says, silicon-based life is physiologically impossible, especially in an oxygen atmosphere. And he's 100% right. To which Spock replies, it may be, Doctor, that the creature can exist for brief periods in such an atmosphere before returning to its own environment. And that is exactly what we saw in The Devil in the Dark. So our lesson from the Horta is that our chemistry may not be universal or fundamental to life, because the Horta is an amazing science fiction example of how we need to be open-minded when it comes to life elsewhere. The things that we assume to be fundamental to life, just because they are universal to life here on Earth, may just be accidents of how life emerged and evolved in the context of our own planet. Which begs the question, if this is the case, how might we hope to detect truly alien life? To find truly alien life, I think we need to develop a framework for agnostic biosignatures. This is a corner of astrobiology that is just beginning to come into its own in the past 2 years. Let me break down these words for you. A biosignature is just a feature that indicates or suggests the presence of life. And we tack on this word agnostic to say that this biosignature is not specific to life as we know it here on Earth, and that it's capable of detecting unfamiliar life forms too. So to introduce my philosophy for agnostic biosignatures, let me turn to another first contact with a wildly different kind of life. This is the Calamarine from the TNG episode Deja Q. These beings are plasma-based, so they're completely different from anything remotely like life as we know it. Let me share the dialogue from this episode where the crew scans the Calamarine and concludes that it is a life form. Worf reports, energy patterns are reading as highly organized, to which the computer says, signal patterns indicate intelligence. The highlights here, patterns, organized patterns, intelligence, are indicative of where I'm going with this, of what I think is important to understand about agnostic biosignatures. And that is that life is complicated, that life is a complex system, and complexity is maximized somewhere between complete orderliness and complete and utter chaos. One might say that life is a system in which information has structured flows of matter and energy, and that structuring leads to complexity that can form the foundation for agnostic approaches for searching for life. So what I'm going to do for you here is share with you 4 examples of agnostic biosignatures that have been developed by astrobiologists in recent years. Now, on this whirlwind tour, we're going to encounter words that sound like technobabble pulled straight from a Star Trek episode, but I promise you they are all real scientific terms, and I'm just so excited to be able to share them with you. So the first of these methods is something called chemometric fingerprinting. This was developed by Georgetown University professor Sarah Stewart Johnson and her colleagues. The idea here is basically to use different strands of DNA as different colored sticky notes. So the more complex your sample is, the more different DNA strands you'd expect it to bind with. So a simple sample, like a non-living crystal, you'd expect will only interact with maybe like 1 or 2 different kinds of DNA. But a complex sample, like the cell membrane of an alien life form, may interact with all kinds of DNA. So in this method, we're basically getting a handle on complexity through the diversity of DNA sequences that the sample interacts with. The next method is the molecular assembly index. This is a strategy that was pioneered by Glasgow University professor Lee Cronin and his colleagues. And it basically asks, how many transformations must I make to construct an object of interest? Whether it's a series of building blocks or letters to form a word or chemical bonds to create a molecule of interest. Basically, we're measuring complexity here as the number of unique steps that it takes to construct a molecule. I like to think of this as the Lego block principle. You know, if you go to the Lego store and you buy a Lego set, and if the instruction booklet that comes with it is super, super thin, you know that's a simple set. But if the instruction booklet that comes with it looks more like a dictionary, then you know you're going to be investing a lot of time, energy, and information processing into creating that final product. The cool thing is that the molecular assembly index seems to be able to differentiate between molecules that only life can make and molecules that can be created without life. What I'm showing you here are 4 different molecules and some of their assembly pathways: ATP, penicillin, tryptophan, and asparagine. All right. All 4 of these molecules are used in life, but life is the only process that is known to be able to make ATP and penicillin, whereas tryptophan and asparagine are simple enough that geological processes can make them too. So there seems to be a cutoff around molecular assembly index 15 or so, where above that, life is the only thing we know that can make those molecules. And below that, it could be life or it could be some abiotic process. Next, I want to share with you a technique pioneered by my friend and colleague Stuart Bartlett at Caltech. Stuart and his team have devised a way to measure the complexity of a planet as a whole. Given a series of observations of that planet over time, you can ask, what is the minimal model required to reproduce the data that you took? In this method, complexity is measured by the size of the model needed to reconstruct your data set. And so what Stuart and his team did was he took a series of observations from the Earth and Jupiter and degraded that data to what would be seen if these were extrasolar worlds far away from Earth. And plotted here is the statistical complexity of those measurements for Earth in cyan and Jupiter in magenta. And what you can see here is that Earth's complexity on average is a good 50% greater than Jupiter's across all of these different wavelengths or colors of observation, and that this may be related to the activity of a thriving biosphere on our own planet. Finally, let me tell you about some exciting work that we're doing right here at the Carnegie Institution for Science's Earth and Planets Laboratory. I'm leading a study with my colleagues Anirudh Prabhu, Jason Williams, Shauna Morris, and Bob Hazen, and many others on how to interpret the network topologies of planetary atmospheres to get a handle on their complexity and to look for signs of life. What I'm showing you here are networks of different planetary atmospheres: Titan, Venus, early Earth, and modern Earth. And the nodes or circles that you're seeing are different chemicals in those atmospheres that are linked together by reactions. The color and size of the nodes tell you how important that particular node is to the network as a whole. And so what we're trying to do is find a way to get a gauge on complexity through the structure of the relationships among the molecules in an atmosphere. And what's really cool is that our preliminary work has shown that you can actually differentiate Earth's atmospheric network topology from that of other planets in our solar system. And not only is Earth's network different from those of other planets, but it seems to be more similar to living networks. So on the bar graph that I'm showing you on the right, Earth's network's homogeneity seems to be different from that of other planets and more similar to those green bars, which are a metabolic network from a cell, a neural network from the brain, and a marine food web network from obviously a food web, an ecosystem. So as somebody who studies planetary atmospheres and their coevolution with life on a planet, I was incredibly struck by this moment in Star Trek Discovery, where the crew is struggling to communicate with the enigmatic species 10C. Remember, these are those gas giant dwellers who communicate through chemical pheromones. And there comes this moment where the crew needs to tell the 10C, "You are hurting us." But they're struggling with how to convey the concept of us. And they bounce around various ideas, maybe send them the number 6, because 6 is the atomic number of carbon. But that might be a little too vague. Maybe send them the DNA sequence of one of our humans, but that might be too specific. And that's when Captain Michael Burnham has this amazing insight. She says, the air, the exact ratio of gases we need to breathe, 78% nitrogen, 21% oxygen, 0.93% argon, 0.4% carbon dioxide. They will recognize that as us. And here's why I think that is so beautiful, because the chemical composition of our atmosphere is a reflection of billions of years of coevolution with the biology on our world. It is an ambassador to the cosmos for this complex, dynamic, persistent, and innovative process that we call life. It is a signal to the universe that we're here, that we exist. And the 10C knew how to read this message and divine the hidden complexity in these numbers. And I'm trying to make sure through our research at Carnegie that we are capable of doing that too. So I know we're almost out of time before we need to bring on our glorious panel. But before we transition to that, let's try to put our knowledge here to the test. And let's do that by bringing things close to home through Star Trek Picard's second season. This season takes place in the year 2024, just a few years from now, in a city called Los Angeles. Our heroes from the future have come back through time to ensure that the launch of a crewed mission to Europa proceeds as planned. This is René Picard, one of Captain Jean-Luc Picard's distant ancestors, one of the astronauts on the Europa mission who is destined to find evidence of the first alien life known to humanity. So let's say that you are René Picard. What are you going to look for? Well, just as a reminder, Europa is a moon of Jupiter and a prime astrobiological target. In fact, NASA is currently constructing a mission called the Europa Clipper mission. This is a real-life mission to go to this moon and search for signs of habitability and inhabitants. Europa is a so-called ocean world because beneath its thick ice shell hides a vast global ocean of liquid water. Not only does it have liquid water, we think that it has the right fluxes of reductants or food from hydrothermal vents and oxidants or quote unquote air from the radiolysis of its ice surface that could support a thriving biosphere underneath of that ice. Remember, life is flux. You've got to eat and you've got to breathe. And yes, you need to excrete too. So the gases that life exhales may be a good biosignature. But there's a real big twist to this story. You see, according to Jean-Luc Picard's history books, René Picard is not destined to find life on Europa. She's destined to find life on its sister moon, Io. And my jaw dropped when I heard him say these words, because although Io is an ocean world just like Europa, its ocean is of a completely different nature. Io's ocean is a magma ocean. It is made of liquid molten rock. So any life that exists on Io would be of a fundamentally different nature to that of life on Earth. So again, I put this question to you. If you were Rene Picard peering out your window at Io in search of truly alien life, what would you look for? Now, I realize this is an extremely daunting question, but I promise if you've been paying attention to this lecture for the past 30 minutes, you already know the answer. Number one, you would look for a diversity of chemical components, and you wouldn't discount anything because life on Io would certainly not have the same biochemistry as life on Earth. This is our lesson from the Horta. Number two, you would search for active fluxes of material that corresponds to what life would do on Io, not to what life would do on Earth. This is our lesson from species 10C. And finally, you would look for complexity, structures or patterns that are indicative of functionality that could have only been created by an evolutionary process. This is our lesson from the Calamarine. These are the three things that I think you'd want to look for to identify life as we do not know it. In fact, if I had to venture a guess, these are the three things that a tricorder scans for when it is looking for biosigns, or what you would look for if you were trying to find those precious little life forms from space. Now, look, I am not an official Star Trek science consultant. I have no idea why a tricorder is called a tricorder. But if I had to make something up in my headcanon, this would be it. These are the three elements of agnostic biosignatures. These are the ways that you would seek out new life. And the amazing thing is, scientists are working on them right now. You don't have to wait till the 24th century to be the next Catherine Janeway or Lieutenant Commander Data. You can join us today as we explore space, the final frontier. Your starship is waiting. The future is yours, and I'll see you out there. Now, before we bring on the panel, just want to remind you that if you want to learn more about the science of Star Trek, check out this podcast, Strange New Worlds, the Science of Star Trek podcast. You can also follow me on Twitter at MikeY, M-I-Q-U-A-I. And I want to give my heartfelt thanks to these two brilliant individuals, Dr. Aaron McDonald and Dr. Mohammed Noor, the official Star Trek science consultants, without whom and their predecessors, none of this would exist. So thank you very much for your attention. If you have questions for me, you can type them into the Q&A box in your chat. We'll get to them at the very end. But right now, I'd love to bring aboard our panelists. Panelists, please join me. Awesome. Yes. Hello, everyone. So first up, we have Dr. Anjali Piette, someone whose voice may be familiar. If you've been listening to my podcast recently, she told us all about the way that species 10C's homeworld lost its atmosphere to space and transformed from a gas giant planet into a rocky world. Anjali has a PhD in astronomy from Cambridge University, and her research interests include understanding the link between exoplanet interiors, surfaces, and atmospheres. Welcome, Anjali.
Hi, it's great to be here. Hi, everyone.
Next, we have Dr. Sam Dunning. He has a PhD in chemistry from the University of Texas at Austin. And when he's not watching Star Trek, he can be found in the lab synthesizing new and unusual materials. Sam and I met at a Carnegie Board of Trustees event where, in between schmoozing with famous millionaires, we would commiserate about the lack of love for Star Trek Enterprise. So Sam, it's been a long road getting from there to here. Welcome aboard the panel.
It's good to be here. Hello, everyone. Nice to talk to you.
And another voice you may have heard on my podcast, Dr. Kara Brugman, earned her PhD from Arizona State University. Kara and I share the goal of trying to bridge the gap between solar system science and exoplanetary science. And today, I think we'll learn a little bit more about how she explores the possible compositions of exoplanet magmas. But her personal chemical composition is listed on her website. It's 20% tea, 25% snacks, 10% bouldering chalk, 15% cat videos, and 30%, yes, you guessed it, Star Trek. Welcome, Kara.
Thanks, Mike. It's great to be here.
Yeah. Now, when I was deciding on what grad school to attend, there was one visit to campuses that stood out among the rest. On that visit, I encountered some people who loved Star Trek just as much as I did, and one of them was Dr. Peter Gao. Peter graduated from the same research group at Caltech as I did, 3 years ahead of me, and I think of him as my science big brother, the Spock to my Kirk. Peter, welcome.
Hi, everyone. Great to be here.
All right, so who is excited for some science of Star Trek trivia? Yeah, so that's right. Those of you who are tuning in via Zoom, you're going to get a trivia question that you can answer, and then we're going to go and try to answer them together and learn about some more science in Star Trek. So this is my first time trying to do this, so I hope I don't mess it up, but I'm going to launch the first question now. Those of you on Zoom, hopefully you can see it. I'll read it out loud as well. So trivia question 1 is, in Star Trek for the Voyage Home, Montgomery Scott gives the formula for a far future material to a 20th century manufacturing company. What was that material? A, dilithium crystals. B, Trillium-D, C, duranium, or D, transparent aluminum. While you're answering that, let's get to know Sam Dunning a little bit more. Sam, could you tell us about a little bit about your personal and scientific connections to Star Trek?
Yeah, my personal connection would be, I remember just as a kid, my dad had all of The Next Generation on VHS. So I was very impressed at first, just the sheer number of VHS as a child. But then when I got older, we would watch The Next Generation and Voyager, and then eventually Enterprise when that began to air. And it was Star Trek has really been like a bonding thing with me and my dad, and watching it together and talking about it and discussing the highs and some of the lows. Some Nemesis, not the best. But yeah, and then scientifically, I'm a materials scientist. There's a lot of fantastical materials on Star Trek. Dilithium, what is the warp core? I used to watch it and think, what is the warp core? What's it made out of? And I suppose in some ways that has influenced my scientific journey to try and find these new materials with these strange properties that you see on science fiction, and try and make them reality.
Yeah, absolutely. There was like a little blip on the dilithium crystals answers after you said, what is the warp core made of? So that was really funny. I'll give you 10 more seconds to answer this question. Get those answers in before we close the poll and look at the results. 5, 4, 3, 2, 1. Just guess if you don't know. There's no prize. Honestly, there's no incentive, and also don't cheat. Like, I know you're all at home on your computers, but please, this is just for fun. All right, I'm going to end this poll and let's share those results. So it looks like, dilithium crystals were quite a bit of the folks at a third of the population answering that question, but the overall answer from the audience was transparent aluminum at 51%. And that is the correct answer, transparent aluminum. So let me stop sharing this poll here. Give yourself a round of applause if you got that one correct. Sam, is transparent aluminum a real thing?
Yeah, well, I'm going to share my screen if that's okay.
Yeah, on screen.
Yeah. So hopefully you can all see here the moment from the voyage home where Scotty shares the secrets to transparent aluminum. And if you can see there on this very old Macintosh, it's meant to be a mixture of aluminum, silver, hydrogen, which I don't know, they may be taking some liberties there on the science of the bonding of those elements, but the answer is yes, it does exist. Though in reality, it's a much more complicated structure, but there is a material called aluminum oxynitride that companies manufacture and sell and brand it as transparent aluminum. And true to Star Trek, it is one of the hardest materials of its kind. It's used for things such as optical devices and bulletproof protective glass. But I don't know if they've tested it on photon torpedoes just yet. I don't know if we'll be able to make starships out of it. But Star Trek was right on the money here. There is a form of transparent aluminum that is incredibly hard and incredibly resistant to, like I said, bullets and other projectiles. So they were right there. And you know, as this relates to my work, I research the behavior of materials at extremes. So this material, transparent aluminum, is synthesized under some funky conditions. You need to use an inert nitrogen atmosphere and heat mixture of the aluminum and other precursors to thousands of degrees Celsius to get aluminum oxynitride. I research how extreme pressures affect materials, and when I say extreme, I mean pressures that are hundreds of thousands times that of Earth's atmosphere. And when we do this, we can make materials like aluminum oxynitride or transparent aluminum that have these seemingly fantastical properties that we see in Star Trek. Again, some more here. We have type 6 and 9 shuttles that have the tritanium hulls, or the class F shuttle that has a germanium hull, that are incredibly hard materials, ultra hard alloys. And while on Star Trek, they have the luxury of flying around the galaxy to find planets where all these alloys occur naturally. In the lab, I try and find ways of making analogous materials here on Earth and seeing if we can do it.
Cool. So Sam, what are you working on in the lab? I know you're working on something that is sort of like transparent aluminum, but is also very, very different.
Yes, it is. I make my own spin, I guess, on transparent aluminum. I work on what sounds incredibly fantastical, flexible diamonds. So we make these by taking small molecules that stack quite, in these nice rows. Think of like a stack of pancakes, right? Each one of these molecules is sat on top of the other. And if we put force on those molecules, we can cause a solid state reaction to form this long chain of diamonds, a diamond-like core. So these carbon-carbon bonds are exactly the same as those you would find in diamond that you all know and love. But they are only in one direction, as opposed to conventional diamonds, which have these carbon-carbon bonds in all three directions. And if you just think of a normal wire, if you make this chain of diamonds long enough, you should be able to bend it and flex it. And these materials are predicted to combine the incredible properties of diamond, the strength, the chemical and thermal stability, with the flexibility of conventional polymers like polystyrene that you come into contact every day. And to do that, we use what's called the diamond anvil cell, which is here on the left. And to exert these huge pressures required for these reactions to occur, we have to squish the molecules between the tips of diamonds. So this is a picture of a diamond anvil cell to the left, and zoom in there on the actual tips of the diamonds, where we put a little bit of sample, a ruby to control, to measure the pressure, so we know how many hundreds of thousands of times atmospheric pressure we're at. And from that, we can do a whole host of various characterization techniques and find out if we're making these flexible diamonds. And we can also scale them in the lab using various other methods, Paris Edinburgh press there in the center, and multi-anvil press. So we can actually make, hundreds of milligrams at the moment of these materials, but enough to play with to fully characterize, to gain a deeper understanding of their properties and what we can use them for. And on the subject of what we can use them for, is this the next question?
Absolutely. Go.
Yes.
Real quickly, tell us what in the world is a transparent diamond, a flexible diamond useful for?
Yeah, so there's a lot of theorized uses, wearable fabrics that are diamond-like, so incredibly resistant protective fabrics, things like that. One of the pie in the sky ones, and this is how we link back to Star Trek again, is a space elevator, is one that has been well proposed. And for those of you who can potentially, props to those of you who can remember this deep cut Voyager reference, but Star Trek again has predicted that such a thing would exist. So if we look here, this is Voyager season 3, episode 19, Rise. And this is wonderful, CG work that is meant to be a planet with what they class as an orbital tether, but is the same thing as a space elevator. And the point of having a space elevator would be because, we're very good at launching rockets into space, but in theory, if you have a space elevator or an orbital tether, you can just climb up the orbital tether and not have to use giant rockets and burn all that fuel to get up into space. You can just climb up the tether and then eventually break the pull of gravity and get into space. Though Voyager does also have a warning for us that there are a number of OSHA violations that are potentially there with a space elevator. So, it is a cautionary tale, but as you can see here, although this poor person is falling out of the space elevator, you can see the pod that they would climb up in, and as it's going up into the atmosphere and climbing up into space, and you use it to transport whatever you wanted up to your space shuttle.
Awesome. Thank you so much, Sam, for sharing a little bit about how your material science research relates to Star Trek and the possibility of space elevators. How cool is that? I'm going to open up the next poll for us. So here we go. The poll question number 2, our trivia question number 2 reads, in the TNG episode, The Chase, we discovered that an ancient species of preservers seeded terrestrial planets with the building blocks of life. What is the scientific term for this process? Is it A, polyploidy, B, horizontal gene transfer, C, panspermia, or D, abiogenesis? As you're answering that, let's get to know Kara a little bit more. Kara, tell us a little bit about your relationship to science and Star Trek.
Ooh, well, I first encountered Star Trek flipping randomly through channels on the TV when I was a kid. So I happened to see an episode of Next Generation, loved it, and it was all over for me after that. I was a huge Star Trek fan. In fact, if you come over to my apartment anytime, probably Deep Space Nine is playing on the television as background noise. And one of the things that affected me most about Star Trek in terms of my science today is the depiction of scientists that they showed. So I would say until recently, the depiction of scientists in media has been pretty homogenous, shall we say. So it was really inspiring as a young woman of color to see all different types of people and species, scientists who were respected by their colleagues and who were doing great work in amazing science.
Absolutely. Thank you, Kara. All right, 10 more seconds to get your trivia answers in. This is a fun episode. I always enjoy going back to watching The Chase. So 5, 4, 3, 2, 1, ending the poll and sharing the results. Once again, you all are so smart. 55% answered panspermia, and that is the correct answer. Panspermia is the idea that you can have life originate on one planet and then travel from that planet to another to seed it there. In particular, in this episode, we're talking about directed panspermia because it is an intelligent life form that is purposefully doing this. Although you can also have undirected panspermia through asteroid impacts and such. All right, so let's stop sharing that and talk a little bit about The Chase. If aliens actually tried to do directed panspermia, would the terrestrial planets that they're trying to seed actually be receptive to primitive life, Kara?
That's a good question. I'm going to share my screen too. So we're talking right now, in terms of this picture, about a planet that's very similar to Earth. This is a Class M planet. In this instance, it's at Bajor. And these planets have plate tectonics and a lot of liquid water, much like Earth. So I think, yes, if aliens seeded an Earth-like planet, probably life as we know it would thrive. Now, during your lecture, you did talk a little bit about the possibilities for life in atmospheres, but since I'm a geologist, I want to think about rocky planets specifically, those terrestrial planets. So if a planet is an M class, could life thrive on its surface? Now, that's where the science we do at Carnegie comes in. In my research, I'm interested in whether life can thrive on exoplanets, those planets that are outside of our solar system. I do experiments to see what kinds of surfaces those exoplanets might have. So to do that, I make lava in my lab, and this is a machine I use. It's called a piston cylinder. And here I look at the exoplanet lava's chemical composition that I've made. I'm interested in lava, first of all, because volcanoes are awesome, right? And second of all, because lava becomes the newest surface of a planet. In this image of a volcano eruption, you can see that the lava is already starting to cool and harden into a new surface. We can look at the composition of that new surface and see if any of the organisms we know of are able to survive on it. But we do also know that life can survive in places that we wouldn't expect. So some of you might have heard of extremophiles. Now, these are organisms that live in extreme environments. Now, you might remember that giant tardigrade ripper from Discovery. Now, tardigrades are actually real organisms that can survive being exposed to all kinds of things: outer space, radiation, and high pressures and temperatures. There are also some extremophiles that live around hydrothermal vents that are deep in the ocean. You might have heard these vents referred to as black smokers or white smokers. Now, these are high temperature, high pressure environments that are full of sulfur, not unlike Class Y demon planets, which are supposed to be very hot and very sulfurous. Now, we're learning new things every day about what kinds of environments could possibly support life. And remember, there are classes of planets that I haven't shown you here today that aren't technically habitable by humans, but they can support other species, other sentient species, even in the Star Trek universe, or they could be good targets for terraforming. So would terrestrial exoplanets be receptive to life via panspermia? I'm going to be optimistic and say probably.
Awesome. Thanks for sharing, Kara. That's really cool research that you do. I'm always very jealous of your cool experiments. As somebody who only does research through computational stuff sitting at my computer. You've got an encyclopedic knowledge of Star Trek. What is your favorite example of the scientific method being displayed in Star Trek? You're muted. You're muted.
I think that's Data's Day. That's one of my favorite episodes of Next Generation. It's probably the episode I watch most often. I see something new every time I watch it. And in that one, Data is trying to figure out what caused this transporter accident that killed a Vulcan ambassador. He systematically eliminates all of these possible causes. He works together with Geordi and with Chief O'Brien until he comes to an improbable but correct hypothesis.
Yeah, I love that. My favorite scenes in Star Trek are when a group of people come together and try to solve a scientific problem. They each bring their own little piece of insight or expertise. And that's what we get to do at Carnegie every day, right? These collaborations, they're just so awesome. All right, does anybody else have an instance of the scientific method that they wanted to share before we move on to trivia question number 3? All right, then we are moving on to trivia question number 3. So let's launch that out. Trivia question number 3. In the Deep Space Nine episode, Starship Down, where does the USS Defiant go to hide from a squadron of Dominion warships? A, the atmosphere of a gas giant. B, the corona of a star. C, a dense molecular cloud. Or D, inside of a black hole. And while we are getting your answers to that, let's get to know Peter Gow a little bit more. Peter, tell me about your relationship to science and Star Trek.
Okay, sure. Yeah. So my first time watching Star Trek was sometime during Voyager's run. And I say sometimes because I think I watched it in syndication. And so one day I'm watching a season 3 episode. One day I'm watching a season 6 episode. And I was just so confused about how Janeway's hair just keeps changing between episodes. At that time, I didn't understand that we were actually crossing seasons. I was young. And so that was very confusing. And then sometimes there will be Kes in the cast. Sometimes there will be 7 of 9. And so I was very confused until later on, I finally realized that the show went through some transformations during its 7 seasons. And from then, I essentially followed everything that came out. I watched the finale of Voyager live, the premiere of Enterprise live, and basically everything else after that live. Eventually, I went back and watched the other series to some extent. I will admit that I still have holes where there are episodes I haven't seen yet. There are a lot of them. And currently, I'm greatly enjoying all the new shows. Scientifically, I think I was just blown away by both the science fiction ideas that were espoused in the series, the strange new worlds, as it were, and the diversity of science and ideas that were shown in these series. One day they could be exploring an M-class planet, another day they were exploring a Demon-class planet, for example. And so that kind of, I think it planted a seed in me in trying to understand the diversity of planetary systems, which is what I do today.
You're a planetary scientist.
Yep.
All right, everyone, I'm going to close this poll and show the results. So here we go. Ooh, this was a hard one. So 41% of you answered a dense molecular cloud, but I'm sorry, that is incorrect. The correct answer is A, the atmosphere of a gas giant, which I guess, looked kind of like a very dense cloud because it had clouds and hazes in its atmosphere. It was a very soupy kind of material depicted in this episode of Deep Space Nine. Peter, you study clouds and hazes in exoplanet atmospheres. Is this soupy, opaque atmosphere a realistic depiction?
Well, let's take a look. So I also have slides. This is if we prepared this. I would say yes. And that wasn't the only episode or movie that showed the atmospheres of planets from within. So here are just some examples. Starship Down was mentioned, right? Where the Defiant was chased into a gas giant's atmosphere. Extreme Risk was another one in Voyager, where I believe they lost a probe in another giant planet atmosphere, and the Malon were after it. And so they had to build a whole new shuttle to go and get it. Sleeping Dogs Enterprise, where they went down to rescue some Klingons. And just recently, Memento Mori, or Mori, I don't know, from Strange New Worlds, the Enterprise had to hide inside a brown dwarf or a gas giant. They didn't really make it clear. Where again, it was very hazy and cloudy. And so this was all very interesting to me. My research focuses on the atmospheres of planets and exoplanets. And in particular, I'm interested in the formation of clouds and hazes in these atmospheres because they tend to block our prying eyes from looking deeper into these atmospheres and trying to understand compositions and atmospheric and planetary origins. And so, at first glance, what do you see? A lot of these images show kind of orangey, purpley, brown, dark colors. And this is actually similar to some extent to what we have in real life. So here is a really nice picture showing the planet Saturn and the hazy moon Titan, this brownish thing right in the foreground. And both of these worlds have layers of aerosols or hazes that are a product of photochemistry, which is where simple molecules in the atmosphere gets broken down by high energy radiation like UV photons, and which leads to very complex chemical reactions that form small particles. And these particles just hang out in the atmosphere. And so speaking of Titan, another instance where a starship when no starship gone before is, of course, when the Enterprise hid inside Titan's atmosphere to get to be undetected by Neuro's space starship in the 2009 Star Trek movie. So, from looking at it, it seems like Star Trek's got it right. A lot of these atmospheres are kind of brown and kind of orangey, and like Mike said, soupy. And one reason for this is that a lot of these chemicals absorb UV and blue light, actually. And so what gets scattered out is red light. And that's why they all look red and orange. And so, that's pretty good. Now, in real life, we can't park a starship inside an atmosphere, a hazy one, a cloudy one, or clear one, whatever. I wish we could. But what we can do for planets in our own solar system is to send probes, actually much like what Voyager did in Extreme Risk. And so this is a nice artist impression of the landing of the Huygens probe on the surface of Titan. So this was part of the Cassini mission that took place throughout the 2000s. And when Cassini got to the Saturn system and launched the Huygens probe, it parachuted through the atmosphere, eventually landed on its surface, and took amazing measurements of the atmosphere showing that it is full of these hazes that are likely organic. Now, for planets and brown dwarfs outside of our solar system, what can we do? We can't actually go there. We don't have warp drive, unfortunately. So the best thing, next best thing, is to observe these worlds with telescopes, space telescopes, ground-based telescopes, what have you. So this figure shows the brightness variations of a brown dwarf. And the bottom axis is time. The y-axis, the vertical axis, is just brightness, essentially. And you can show how it varies, and if variations are not regular at all, eventually, essentially, it actually goes, the amplitude gets higher and higher and higher. This was observed using the dearly departed Spitzer Space Telescope. And what they backed out from this light curve is that this brown dwarf had to have cloud bands with clear spaces in between. And the clear spaces where you see deeper down and you get higher, brighter light because it's hot down there. And so they made a nice movie, which may remind you of the Strange New Worlds episode, showing how these different cloud bands and cloud holes crisscrossed each other as this brown dwarf rotated, and that's how they get these variations. So this is, this is still an artist's impression, but it's based on the Spitzer observations. And so what we hope to do here at Carnegie is to use the next generation telescopes to do something similar to characterize exoplanet atmospheres, including their clouds and hazes. And the one that we're really looking forward to is the JWST, the James Webb Space Telescope, which is due to put out their first images in less than a month, and we are freaking out because it's coming so soon. And so, in early July, mid-July, I should say, mid to late July, we'll see our first images and we'll get our first observations of these strange new worlds. So thank you.
Thank you, Peter. It's certainly an exciting time to be an exoplanet astronomer and an exoplanet scientist. Real quickly, you mentioned that you really love the diversity of kind of strange new worlds that has been depicted throughout Star Trek over the past 55 plus years. Are there a couple that you just want to shout out real quickly before we move on to pull trivia question number 4?
Yeah, so I think some of the ones that, we're used to these M-class idyllic Earth-like planets. So, it always strikes me fancy when we go away from that. And so the Andorian homeworld is an icy moon around a gas giant, which, we have icy moons around our gas giants. Maybe they have oceans underneath the ice shells. That's fun. Speaking of water world, there is actually a world that's entirely made of water in the Voyager episode 30 Days. I think that was an artificial planet, but there are potentially water worlds out there where it's not all liquid water. The pressure is way too high at depth. You'll become high pressure ices, actually. But we are surveying these exoplanets to see if any of them are in fact water worlds. So that's just 2 off the top of my head.
Nice. Anybody else want to chime in quickly with a different kind of planet that you've really enjoyed seeing in Star Trek? Going once.
Anything that's not the planet Hell set over and over again.
Wait, what did you say? I didn't quite catch that.
Anything that's not the same planet Hell set over and over again.
Oh, the planet Hell set or Vasquez rocks, right? Nice. All right, let's open up trivia question number 4. This is our last one. And here we go. In the Strange New Worlds episode, Children of the Comet, what does a comet bring to the planet Persephone 3? Is it alien technology, water, a deadly disease, or precious minerals? We'll see how many of you have been keeping up with the latest Star Trek series right here. And while we get your answers to this, let's get to know Anjali Piette a little bit more. Anjali, tell me about your relationship to science and Star Trek.
Hey everyone. So compared to everyone here, I'm a bit more of a newbie to Star Trek. I'm like amazed by how much all of you guys know. I really got into Star Trek, I guess with the J.J. Abrams movies, so definitely more recently. But I think what I love about Star Trek is very similar to what I love about science and astronomy, which is being kind of displaced into this really new environment that just feels very different to what we experience on Earth. And I love the way that Star Trek combines that sense of adventure combined with science. It really reminds me of why I always wanted to be a scientist and that sort of fighting spirit. And for the science side, the stuff that I work on here at Carnegie is exoplanet atmospheres. We're really lucky to be able to get measurements of the atmospheres of planets that orbit other stars, which is kind of crazy. And so I work on interpreting those measurements and figuring out what we can learn about those climates and those other planets.
Fantastic. Yeah, Star Trek is a great show if you're into planetary atmospheres, because as we've been seeing, and I think we'll see a bit more in just a second, there are a lot of cool planetary atmospheres in Star Trek. So I'm going to go ahead and end this poll. Get your questions in 5, 4, 3, 2, 1, and let's see how we did. Very nice. All right. So either all of you, or 46% of you, have been watching Strange New Worlds, or 46% of you know what comets are made of. But good job. The answer is B, water. So Anjali, have we detected water in exoplanet atmospheres for real?
We have indeed. We have actually detected water vapor in more than 20 exoplanet atmospheres. And I just want to pause to reflect on the fact that, how crazy that is, right? Unlike in Star Trek, we're not sending probes to these planets because they're too far away. We can't go and visit them. And yet from distances of, even over 100 light years away, we can tell that there's water vapor in those atmospheres. I think that's amazing. But it is a challenging measurement to make. And that means that most of these detections are in the types of planets that are easiest for us to see at the moment, which are planets that are quite big and quite hot. So for most of these planets where we have water detections, they are what we call hot Jupiters. So they are planets that are around the size of Jupiter or even a bit bigger. And they're hot because they're orbiting very close to their stars, and that makes them more accessible for us to observe them. That said, there is a water observation for a planet that is smaller and cooler called K218b. I'm going to show you some stuff about that later on, I think, so I won't spoil too much now.
Awesome. One of the things that I've been so enjoying about Strange New Worlds, the latest Star Trek series, is that we get these amazing detailed graphics of the planets that we've been going to in Star Trek. The production team just puts in so much amazing work into fleshing out the details of these worlds. Have you seen anything interesting in these data sheets, Anjali?
Yeah, so why don't we take a look? Okay, so hopefully you can see my screen there. So this is one of these data sheets. And when I saw this for the first time, I thought, this kind of looks like some of the planet properties files that I use with my code. Actually, some of these things that we're seeing on this data sheet are things that we really can measure for exoplanets. I should say as a disclaimer, there are also things that we can't measure yet. So on the right-hand side, we're seeing, different kinds of life forms and stuff like that. So Mike, what you were saying in your talk obviously is, some ways that we might be able to detect that in the future. We're not quite there yet, but let's have a look more on the left-hand side here. We have things like the rotation period and the revolution period, so the length of a day or a year, and also the estimated mass. So let's focus on that just for a second. This means if we have the mass of a planet that we can weigh it. So how do we do that? We can't put it on a scale, right? So I'm going to show you how we weigh a planet with this little movie. And so basically, when we picture a planet orbiting a star, usually we imagine the star being fixed and the planet going around it. But actually, both the planet and the star are both orbiting their common center of gravity, which means that the planet is causing the star to wobble a little bit. It's kind of exaggerated in this movie, but that wobbling means that the light that comes from the star also has a bit of a wobble in it that we call a Doppler shift. And the size of that wobble depends on the mass of the exoplanet orbiting the star, which is how we then take that Doppler shift and reverse it and try to calculate the mass of the planet. But another way, another type of measurement that we do to learn more about these exoplanets is what we call the transit method. So it's good to use different methods to put together as much information as we can about these planets. And so this method that I'm about to show you relies on when an exoplanet passes in front of its star relative to us as the observer. So let's play this. You can see the planet passing in front of the star. And when it does that, the planet is blocking out a little bit of light from the planet. So let's just pause it here. The smaller planet, when it passed in front of the star, blocked out a little bit of light, and the bigger planet blocked out a larger chunk of light. So if we sit and stare at a star for a long time and we just see the brightness dipping periodically, we can infer that the planet is passing in front of it as it goes round and round its orbit. And depending on how big that dip in brightness is, we can figure out the radius or the size of the planet. And so those are two really important measurements for us to learn more about these planets. But let's go back to this data sheet. The other thing that I want to point out, which we're kind of talking about with the water, is the atmospheric composition. So on this data sheet, we're seeing there's 79% nitrogen, 19% oxygen. There are some kind of crazy things on here like tungsten as well. Maybe that's a little bit too crazy. But we really can learn about the chemistry of these atmospheres. We're doing that for exoplanets right now. And so how do we do that? How can we look at a planet that far away and figure out what the atmosphere is made of? Again, this is something that we can do using the transit method when the planet happens to be in this really convenient location in between us and the star that it's orbiting. So in this movie, on the left, we have the host star of the planet. Then we have the exoplanet in the middle with its atmosphere, and we're looking at it from the right-hand side of the movie. And so as light from the star passes through the atmosphere of that planet, some of the light goes straight through and goes straight to our telescopes, but some of the light is absorbed or scattered by these different molecules. And we can know how those molecules scatter and absorb light through experiments in the lab and calculations. And so from Earth, we can see, okay, which colors of light are missing from our observations, and we can reverse that and figure out which molecules are in the atmosphere to create that detection. So that's how, for example, we can detect water in the atmospheres. We've also detected other species like sodium and potassium as well, which is really cool. And before, I kind of mentioned a little teaser of this planet called K218b. This is one of my favorites. I thought, well, since that data sheet reminded me of real data that we have, why don't I make my own data sheet for this real life exoplanet that we know of, that we've measured a bunch of stuff for. So K218b is a kind of planet called mini Neptune. Its size is in between the size of Earth and Neptune, and we don't have any planet of that size in the solar system. So it's one of these really funky, cool new planets that we've discovered. And actually, of all the planets, exoplanets that have been discovered so far, this is the most common type. And yet we don't have any in the solar system. That's kind of cool, right? Peter was talking about the diversity of exoplanets and in the universe. That really is true. So we know that the mass of K218b is about 8.63 Earth masses. It's a little bit bigger than the Earth as well, 2.61 Earth radii. And we've also been able to detect the presence of water vapor in its atmosphere. So using that method that I showed in the previous video, we've worked out that the atmosphere of this planet is mostly made of hydrogen, but it could have between less than 1% or up to about 15% of water vapor in its atmosphere. And the James Webb Space Telescope that Peter mentioned before will be returning to look at this exoplanet again, and we'll hone down more information about its atmosphere and its composition. So this data sheet will get even richer as time goes on.
Fantastic. Oh, I love that you made your own data sheet. I hope that Star Trek will venture to K218b one day. And also, you should join the production team for Star Trek. They would really appreciate all that technical expertise. With time dwindling down, I think we should spend the last 10 minutes answering your questions. So I would like to invite our director, Mike Walter, back to the stage to throw us some questions from the audience.
Okay, thanks, Mike, and thanks, panel. That was absolutely fascinating. So here's some questions. Number one, isn't the molecular assembly index essentially how DNA works, essentially organizing information into a long chemical model?
Ooh, that is a very good question. Yes, you could almost say that we are programmable matter in that there is information that is contained in molecules in life that then get read and translated into other molecules. That's certainly a really cool way of looking at things. The molecular assembly index can be applied to molecules of DNA, but it can also be applied to a broader suite of organic molecules. What if life on, say, Enceladus doesn't use DNA as its genetic polymer? We may still be able to use the molecular assembly index as a way to get a handle on whether or not those molecules that we find on distant worlds eventually are from life or not. Great question.
Okay, another question is, rather than using the term different DNAs, why not a more functionally descriptive term like, as an example, misfits, or molecular instruction storage for information transfer? In other words, is DNA just one kind of molecule?
Okay, is this in relation to the chemometric fingerprinting?
I think so, yeah.
Okay, yeah. I think, yeah, so one feedback that has been given to this type of analysis or this type of experiment is that, yeah, you could use different kinds of molecules besides DNA as well as the sort of sticky notes. So a lot of, so I'm not a biochemist, but you can think of all sorts of suites of other kinds of molecules. Targeting and reference molecules are used a lot in our immune system, for instance, to recognize different things, different types of things in our body, and to process them accordingly. So you could use, DNA is something that I think was used simply because, well, not simply because it's a very complex process, but because we have this method called PCR, which can then amplify the amount of DNA in the system so that we can get a better signal to noise on the final result. That's something that may not exist for these other classes of molecules. And so I think that's why DNA was used here. But that's a great thought. And yeah, we should definitely widen our reach of different molecules.
Okay, the next question. What do you think of the Fermi paradox, which basically says if there are a lot of intelligent transmitting civilizations in our galaxy, why haven't we detected them yet? Do you feel those kinds of civilizations may be very rare, or for some reason we can't detect them?
Ooh, what a question. First of all, nobody knows the answer to the Fermi paradox. There are many potential answers out there. One potential answer is something that my colleague Stuart Bartlett and I wrote about recently, where you can maybe come up with these scaling laws that show that civilizations, as they grow in size, in energetic usage, and in information processing, may reach a barrier in which they necessarily need to stop growing and reorient themselves to prioritize, instead of infinite and unbounded growth, which is unsustainable in the long run, something that is more homeostatic in priority. So we called this asymptotic burnout and homeostatic awakening. That one possibility may be that once civilizations invent technology, they invent they invent ways to burn themselves out, but then they may also invent ways to realize that they're on that trajectory and reorient themselves consciously. That's just one idea out there that you can go and look up. There are plenty of other ideas for how to solve the Fermi paradox, and I think that it's an open question still.
Thanks. I love the term asymptotic burnout. When did aluminum oxynitride come into being? Was it before Voyage Home or after? In other words, does sci-fi inspire us humans to do things that we wouldn't do otherwise? It's a great question.
Oh, I think sci-fi undoubtedly, encourages scientists to investigate things and answer questions that they otherwise wouldn't do. It's scientists are very creative people, but so are writers and all the people behind science fiction. And I think they can ask questions that we wouldn't necessarily think to ask, and challenge us in those ways. And in terms of which came first, I believe the patent for aluminum oxynitride was in 1980, and Voyage Home was 86. So I bet there was a scientist watching that movie who was very, very happy about how they could rebrand their research after they get out of the movie theater.
Thanks. I love this one, especially since it's past dinner time and I'm hungry. I'm wondering about the likelihood of food synthesizers being possible. I don't know if we'll have an answer to that one, but anybody want to take that?
So, there's a whole revolution in terms of 3D printing these days, where you can, create a lot of materials through and objects through 3D printing. And I believe, again, I'm not a food scientist, but people are thinking about 3D printing organic things. And so we may be able to print out our food, so to speak. In Star Trek, we have the idea of the replicator, which assembles things sort of atom by atom. I view the replicator technology as very similar to both the holographic technology and to transporter technology. One key aspect of those is that you require what they call a Heisenberg compensator to compensate for the Heisenberg uncertainty principle. Because if you wanted to build something atom by atom, you need to know the positions and velocities of all the atoms, but you can't know that both of those things at the same time due to Heisenberg's uncertainty principle in quantum mechanics. So I once asked Mike Akuda, who wrote the Star Trek Next Generation Technical Manual, how does the Heisenberg uncertainty compensator work? And he replied, it works just fine. Thank you.
Thanks, Mike. Okay, we have AUs, astronomical units, for the distance of Earth from the sun, and sols for a local day, as distinct from Earth Day. Why aren't there units for size or radius or density and mass that compare to other planets rather than Earth, or other standards?
I guess it's kind of a matter of convenience, right? We're all, different scientists working on different aspects of astronomy are working on things of different sizes. And it's true that we'll use a reference that's relevant to roughly the kind of size we're thinking about. So if you work on planets that are closer to the size of Earth, you'll use the Earth radius as a reference. When we're working on planets that are more similar to the size of Jupiter, we'll use Jupiter's radius as the reference. But it's really useful to have some standards like that, so that when we compare our work with other people's work, it's just quicker to tell the difference between the numbers.
Thank you. Okay, here's one. Other than carbon and silicon, what other element has the next probability to provide a life form? Love that one.
No idea. You can think about life as we don't know it in different media, though. So, for instance, all of life on Earth uses water as its universal solvent. But I love thinking about Titan, for instance, because on that world, there are stable bodies of water on the surface of that moon of Saturn. But on Titan, that liquid is liquid methane and ethane with a little bit of nitrogen dissolved in it. And so it's a very different scenario, but you can still come up with hypothetical biochemistries that would form cell-like membranes in that solution and perhaps have an emergence of life.
Just a couple more here. Do you think our Earth is en route to an asymptotic burnout? And would we realize it in time to reverse course?
Who's asking these questions? I think that's something that we need to study and that we need to take into account, that we need to be very serious about thinking, because we are currently in what I call a major transition in evolution. There have been many different major transitions in our biology's past, from the emergence of information processing inside of strands of RNA and DNA to cells, to complex cell forms, to multicellular life. These are all transitions that are very sudden leaps in complexity. And right now, through our technology, through what we are doing right now with communicating via Zoom or YouTube over the internet and trading ideas with one another, we are in another major transition in information processing. And where that may lead is very difficult to know. I always like to draw the analogy, could a colony of bacteria have predicted a multicellular life form? Could a colony of ants have predicted human civilization? What can't human civilization predict? I think that is something that science fiction actually has a big role to play, in that the mind of a science fiction author is like the mind of a scientist. Before we begin an experiment, we need to think, okay, what if I change this parameter or this thing in my experiment? What do I think will happen? And a science fiction author does that same kind of hypothetical process just in their minds. They say, what if civilization was like this on that other world? How would that culture develop? And what would it be like when we visited them? Things like that. It's actually a very similar thought process.
Okay, one more as we're heading to the top of the hour here. I love this one. Maybe all of our panelists can chime in on their thoughts. What percentage of science shown in the various Star Trek shows did they get right?
47. That's my answer.
I think they get the spirit of the science right. And I think for a science fiction show, that's the most important part.
I think we need a time scale in here as well, because part of me thinks, okay, maybe some of these things aren't real yet, but maybe they will be in the future. So maybe actually the real percentage is bigger.
Sliding scale. Good point. Sam, what do you think?
Yeah, they do a nice trick in Star Trek and other science fiction where they give these ultra hard alloys a name, and okay, maybe that ultra hard alloy doesn't necessarily exist, but like transparent aluminum, it wasn't exactly what they drew up on the screen, but there is an ultra hard form of aluminum that you can synthesize in the lab. Right. And if you want to be generous, then yeah, they get a lot of it right. If you want to be real harsh, then some of these alloys they talk about don't really exist. So
again,
0 points.
They've got the spirit right.
Exactly.
Peter will give you the last word.
Okay, well, I'll just echo Kara then, because I also think they got the spirit right, and also, I mean, the fact that they have science consultants and that they try to put kind of what's the current day understanding in it. Is really special. I was actually looking forward to them putting in more exoplanet stuff in the new series, because the new series premiered after the exoplanet revolution, essentially. I mean, before that, the last thing that happened was in 2002, and we knew like 10 exoplanets then. We know 5,000 now. And so, with Discovery mentioning impact erosion of atmospheres, strange new worlds, brown dwarfs, and accretion disks of black holes, I think it's just fantastic. So, correct or not, I mean, there are definitely parts that are interesting, but the fact that they even named these, I think is incredible.
Yeah, I'm impressed at how well they do. I just want to thank Mike and our expert panel for taking us on a fantastic voyage. It was absolutely wonderful. And I think this is the end of our night, and I'll just say, live long and prosper. Good night, everyone.